Okay, here you can see we've got the F equals BIL investigation, and if you change the current on here, you can see that the force is going up. It's measuring mass, but of course it's really a force, so we can convert that back into a force. If G is going up with current increasing, 5 amps there, if G is going up, it means that top pound balance is being pushed downwards. So if that's the case, the force on the wire must be upwards. But we're measuring the size of the force here. So simple apparatus, nice smooth power supply there, and that's giving us quite an accurate value, so we don't need to use a meter. And then, as you can see, we're investigating F equals BIL, so is F proportional to the current is what we're focusing on here. We've got a diagram there with the wire going between the magnet. Don't move it during the experiment. And this is from the top, a plan view there. And you can see the field will be going this way, which is horizontal, and the current's going this way. And in that case, the force, Sloane's left-hand rule will tell us the force will be out of the board. Results table, we want current, mass, reading, and force. And we can convert the mass into its equivalent force, mass times 9.8 over 1,000, to get that force in newtons. Then we're going to graph up the a nice graph of force, which we can have force in newtons against the current, because we were changing the current. So that's our independent variable. And of course, if they are proportional, don't do a false origin. So we want 0 and 0 there. And lots of readings, hopefully. Hopefully nobody moved it during the experiment. And we should get a straight line through the origin, but don't force it through the origin if it's not. Line of best fit is what we need there. Once we've got that line of best fit, because we know that F equals BIL, or we suspect that's the case, our control variables here, well, B stayed the same, and also the length stayed the same. Remember that our length is 0.050 meters, 5 centimeters. So that means that force equals current, and that the constant in this is B times L. So we compare that to Y equals mx plus c, but the c is just 0. So we should find that the gradient is m. So on this graph here, take the rise in F, so that's the change in F, and here we've got the change in the current. And if we do that, then we should find that we get the gradient, and the gradient is going to be equal to BL. And of course, if the length was 0.050, then B is the gradient of 0.050, and that gives us the magnetic field strength in Tesla. Okay, and that's interesting because, you know, it's quite a difficult thing to measure, the field strength between these two magnets. But there's a nice way of measuring how strong that field is in Tesla. So report what you find there. Also, how straight was the line? So discuss the scatter of the data. Was it widely scattered? Were there any anomalies? Someone did move the apparatus, so are any of these perhaps where they shouldn't be? And did it go through the origin or not? How close was it? The results are here. So you've got written down very neatly, and we'll take a picture of those for you as well.